Hey, let's do a couple of problems on fluids. Let's say I've got a cylinder with water in it, and maybe this is a depth of 20 centimeters. Let's say the radius is 5 centimeters. How much does all that water weigh? Well, we've got an mg for the water going down. What's it weigh? It's going to weigh the volume times the density times g. That's how much the weight is. Volume times density should be the mass. How do we get the volume? It's going to be we're going to have the area at the bottom times the h, and the area, in this case, pi r squared, h, that gives us the volume, density, there you go. Now that is going to be the weight of the water. That's 15.4 newtons. Now, what's the pressure? The pressure is the force per area. So you have 15.4 newtons per that area, that's the pi r squared, and we're going to get a pressure of 1,961 about, and that's newtons per meter squared. Now, what happens if we change the shape of the container? What if we go like this? It's the same depth, okay? Will I have a different pressure? The book says that the pressure at the bottom is equal to rho GH. Doesn't seem possible. Why? Because you've got less water to hold up. But I remember Bryson, he said, the normal force of the wall is pushing like this, and it's got a y component and an x component. That y component pushes down, making up for the difference in the less weight of the water. So that's an interesting point to keep in mind. Now somebody said, so if you had water at all three, the same level, this one's pushing inward, giving it some extra weight down. What are these walls doing? Hey, they're holding up the water. So you still end up, it's amazing how this works. You still end up with the same pressure at the bottom. Pressure is rho GH. Now, what would happen if we connected all these things with a tube? Would one level go down and another go up? No, it's all the same. I gave the example of a milk jug with the handle. When the milk is that level, it's the same level over there. So no difference. Well, that led us to the hydraulic press. If I push down with F1, how much weight can I hold up over here? Depends on the diameters of these pistons. The pressure here has got to be equal to the pressure there. It's all one fluid, the pressure is distributed like that. So we can say that the pressure is equal to force per area, and that pressure is equal to force per area. And then, of course, you can set them equal to each other because you know these pressures have to be the same. So if one area, if this area now is, say, 10 times larger than this area, you'll be able to hold up 10 times the force. Well, some genius asked, I think it was Dan Mayevsky, what if you push in with a certain distance over here? What about work? The amount of work done over here is going to be equal to the amount of work done over here. So what do you know about the distances then? If this force is way bigger, that distance is way smaller. So you go back to your mechanical advantage stuff that we learned ages and ages ago. So how much stronger does this machine make me? It's F2 over F1. So now we'll talk a little bit about buoyancy. We're going to go back to the scale with the water and the little object inside here. So let's say we have some string and we're lowering this into the water. Could we draw a free body diagram for that weight? we've got mg going down. We have tension going up. And the water is being displaced, so it pushes up on here too, and that's the buoyant force. If this object's not moving, we're going to say that the force is going up equal the force is going down. The force is going up will be T plus the buoyant force, and that's going to be equal to the force is going down, the mg. Now, how do you know what that buoyant force is? That buoyant force is equal to the weight of the displaced fluid. I guess we should do a problem on that too. So I don't know why, I don't really need to plug in a bunch of formulas for you. I think you can see the idea on how all this works. Oh yeah, and if there is water pushing up on that weight, let's draw a free body diagram for the water. Here comes the water. If there is a force pushing up on the weight has to be pushing down on the water. What's keeping the water from falling? Well, we've got to have the floor of the beaker pushing it up. So there's a normal force. Plus you have the weight of the water. What this means is that if you put this whole thing on a scale, if the water's pushing up on the weight, that means the scale is going to have a larger reading because this weight is pushing down on the water, which in turn pushes down on the scale. So why is there a buoyant force in the first place? Well, let's just submerge something in a water here. Let's give us a little rectangle here. And we're going to calculate the pressure on top of this box. And let's just say that's the length and the width, and that's the height. How much pressure is here? Well, that's going to be, we've already figured this out, rho g, I'll call that H1. How much force is on here then would be equal to the pressure times the area. Now down at the bottom, you've got a force acting on here too, and that would be the pressure 2 times the area. Well, that pressure is going to be bigger than this pressure because we're further on down. Pressure 2 is also rho g, but it's going to be an H2. So my force 2 is going to be equal to rho g H2 times the area. This up here is going to be equal to rho g H1 times the area. Well, what is the difference in that force? We're going to have a force, F2, bigger than F1. That's the difference in the force. F2 is going to be rho g H2 times the area, and F1 is going to be rho g H1 times the area. Well, there's a lot of stuff that we can factor out here. Rho g times the area minus, parentheses, H2 minus H1. Area times the height. This is this height, that's capital H. This is the volume of the object. That's how much water was displaced. Take the volume times the mass, and you're going to get, take the volume times the density, you're going to get the mass. This is the density of the water. So that's the mass of the water. This is the weight of the displaced fluid. That's how you calculate the buoyant force. And that's what we used when we did the barge lab, that wonderful penny. How many pennies could you fit in the aluminum foil lab? And we were given a sheet. of aluminum foil, 10 centimeters by 10 centimeters. What is the most pennies that you could put in there? We had to say, oh, well, we're going to fold this thing up, right? And I think you remember what we all talked about, that the weight of the pennies would have to be equal to the buoyant force. And that's going to be equal to the weight of the displaced fluid. And again, that's going to be the density times the volume of the barge times G. That is the weight of the displaced fluid. What is the volume? Well, let's give this a Y and an X. So the volume is going to be X squared times Y. We're going to say this is X, and this height is going to be Y. And so I think that gives you an idea of what we did to get the weight of the displaced fluid. And of course, to optimize this thing, you have to do a little calculus and figure out what's the maximum volume you can have. Now, what about Bernoulli's law? All right, so this is the one where we had the pipe that went like this, came narrower, it went like that, and we had a force here. And this, if you shove water in here, it could come out that end. That's a force 2. And so we have a certain distance that this water will get pushed in with. This is like a piston. And then this is going to be a certain distance. The water will come out up there. And we had the height. And we have a velocity going this way. And we have a velocity going this way. So the water comes in, funnels down, goes faster. We're going to increase our kinetic energy. We're going to increase our potential energy. You know what I really ought to do? I'll make it all the way down to here and call that H initial, that H final. So we're increasing our potential energy. We're increasing our kinetic energy because it's going faster. It's squeezing down. It's got to go faster. Where's that energy coming from? The work done. If we do any work going out, well, then that's an issue on that side of the equation. So what did this all work out to be? Conservation of energy is where it comes from. Turns out that the pressure at the initial plus 1/2 rho one half rho V squared plus rho GH. These are all the initial conditions. That's a constant. Or we can, because it's conservation of energy, that's what it's all based on. All of this is equal to a constant. So we can say that the final pressure plus 1/2 rho V final squared plus rho GH final is all equal to that stuff. All right, I wrote it a little neater. Let's say we have a certain volume going into the pipe here. How does that compare to the volume coming out? It's got to be the same because there's no other place for the liquid to go. So this is going to occur in a certain amount of time. That will occur in a certain amount of time. And the volume per time is the flow rate. So let's figure out what the flow rate is. Volume could be thought of as an area times a distance. So imagine you take that area, multiply by that distance, divide by the time. What do we get? Group that together. It's the cross-sectional area times a velocity. And that's your flow rate. All right, we'll do a problem. Let's say you got a pipe here with this is a radius of 8 centimeters. The flow rate is 0.1 cubic meters per second. That's how much water we want flowing through here. So how fast will this be going? What's the velocity? So the flow rate is equal to the area times the velocity. And we calculate the area, pi r squared. We do this, we get a velocity of 4.97 meters per second. Okay, so now all this water is going to get squeezed down. It's got to be going faster up here. R is now 4 centimeters. So what's going to be the velocity up here? Well, you got the same flow rate, don't you? The same flow rate is equal to a different area times a different velocity. So the velocity is going to be 19.9 meters per second. And that makes sense because it's 4 times greater. Why should the velocity be 4 times greater? Because the area is, the radius is cut in half, which makes the area cut to a fourth, which means the velocity's got to be 4 times bigger. All right, now let's work with the rest of the equation. Let's just say this height is going to be 0. And we're going to raise this thing up, say maybe 25 meters. The water that's coming through here is gaining potential energy. And that's going to be determined with this part of the equation. The initial height is going to be 0, so that's going away. Let's calculate the final potential. When I call it potential energy, it's really potential energy per volume. That's what this is. You get 245,000 newtons per meter squared. Now, how do I know that the units are newtons per meter squared? I'm not going to, keep trying to prove the units. Rho GH was pressure. That's pressure. Everything's going to have to be in those same units. Okay, so now we can calculate the kinetic energy using the next equation, the next term of the equation. Let's calculate that kinetic energy, and we'll calculate this kinetic energy. Okay, so I get 200,000 for this term. (200,000 newtons per meter squared there. Over here, I'm going to use 5 meters per second, and I'm only going to get 12,500 newtons per meter squared. Hey, that's interesting. Why is this number so much bigger? Well, first, the velocity is going up by a factor of 4. But the velocities are squared in these terms, so 4 times 4 is 16, and you end up with 16 times your kinetic energy. Now, where is the energy going to come from to make this happen? If this water is just squirting out into the air here, there's no real pressure we're pushing against. The air there is the same as the air over here, so that pressure difference is 0. So let's just say that we're not pushing against anything. All of it's coming from that pressure down here. So how much pressure must I have at the bottom of this pipe to make this work? I get 432,500 newtons per meter squared. So a pump would have to generate that much pressure inside the bottom of this pipe to make this happen. And we talked about how that works with, say, for example, a ping pong ball floating on a stream of air. So if you have the blow dryer and it comes shooting up, the air goes around it like this. The velocity is actually higher here. The velocity is slower here on the outside. In the stream here, the velocity is fast. So when the ball starts to move out of the stream, it bounces right back in. Well, how do I know? Well, it's Bernoulli's law again. If we say pressure 1 plus 1/2 rho v squared plus rho GH is equal to pressure 2 plus 1/2 rho v2 squared plus rho GH. We're not changing our height. That goes away. But the velocity is changing. So if this is 1 and that's 2, we can see that if the velocity slows down, the pressure will increase. And so the air pressure out here is actually higher than the pressure in the stream. So if the ball starts to come out, it tends to bounce right back in. And we talked about how that makes the ball stay in the stream even if the air is blowing at an angle. you would certainly think the ball would just jump out. You should try this at home, get a blow dryer, put a ping pong ball in there. The ball tends to fall out, but then it bounces back in. And how come? As it starts to drop, there's going to be a pressure back in there. Now, what's interesting is the air is curving like this, and there's really a normal force pushing this way from the Bernoulli effect. So this force pushing this way has to come in at an angle, because the air pushing against the ball pushes this way. So we've got this push this way, and we have gravity going down. Hey, all three of these forces have to add up to 0 if this thing's going to stay put. So as this thing comes out of the stream, the force goes this way, and its x component cancels the x component of that guy pushing forward. Of course, the y components hold the whole thing up. What's that got to do for airplanes? Airplanes have a special wing design. The top is longer than the bottom. So when the plane is flying through the air on the top travels a further distance than the air on the bottom. It separates and merges. This air is going fast. If that air is going faster than this air, we can see that there's going to be a pressure difference. Use Bernoulli's law to calculate that pressure difference. If you know this velocity and you know that velocity, you can calculate the pressure terms on each from the top to the bottom. Don't worry about the height difference, because that's so small, that'll be insignificant. But if you can calculate the change in pressure, that change in pressure would be equal to a force per area. And the area I'm talking about is this area here. And you can just imagine all of the little forces here holding the plane up, and that's your lift. And of course, another application we talked about was the peeing tube lab. And let's just say this was H. As that water has pressure here, it's going to push the water out. We're going to get a velocity in the stream. And the range was what we needed to find. The range was Vx times T. How do you get the velocity? Hey, Bernoulli's law. Pressure 1 plus 1/2 rho V squared plus rho GH equals pressure 2 plus 1/2 rho V2 squared plus rho GH again. But this H I'm going to call 0 height. I'm going to make that 0. That goes away. The velocity of this water draining here is going to be very slow compared to that velocity coming out. If we can make an assumption that this is wide and that's going to be therefore slow, then I can get rid of that. It's an approximation. It's not exact. With that in there, the problem becomes a little harder. Now, what about the pressures? We have air pressure over here, don't we? And we have air pressure out here. Well, those pressures are going to be equal too. Okay, you're going to say, yeah, the air pressure down here is a little greater. It is. It's insignificantly different. It's insignificantly, doesn't matter. All right, now what about the rest of this jazz? We're going to left with rho GH equals 1/2 rho V2 squared. What about those rho's? The density cancels out. Bring the 2 over. 2GH square rooted is the velocity. Oh my gosh. That's because it's just based on potential energy. You have potential energy turning into kinetic energy. That's what this is all about. Of course, you have to know what this is all about here. Like the hole is a certain size up, and then how do you get the range? You use the projectile motion stuff from eons gone by. Well, there we have it. I guess that ought to help you.